Alrighty guys, let's go ahead and take a look at this problem we got here. It says we have the planet Venus and it has a mass of 4.87 times 10 to the 24th kilograms and a diameter, that sounds interesting, of 12,104 kilometers. So this is super important that it's giving us diameter and it's giving it to us in kilometers. We'll come back to that later. The center of Venus is located a lot of kilometers away from the center of the sun. The sun has a mass of 1.989 times 10 to the 30th kilograms. Put all answers in scientific notation. All right. So first thing we want to do is calculate the centripetal force that keeps Venus orbiting the sun. So if we're trying to figure that out, maybe we first need to think, what is this centripetal force that keeps Venus from orbiting the sun? And if we were to draw a diagram really quick, we would have Venus, and then we'd have the sun. And we know that Venus is moving around the sun in this orbit, like we said before. Why is it moving around the sun? What force is pulling it towards the sun? Well, that would be forced gravity. So forced gravity is pulling it towards the sun. So now that we know what that centripetal force is, we can go ahead and use the appropriate equation. We have our universal law of gravity right here. So let's go ahead and use that. So for number one, I'm going to write my equation again. Fg is equal to big G m1 m2 over r squared. So first thing we need to do is identify what all these variables are. We know that big G is a constant and it's always going to be 6.67 e negative 11. Next, we need to figure out m1 and m2. So the two masses that we're concerned about are Venus and the sun. So let's just say that m1 is Venus. It doesn't matter. We could have made m1 the sun as long as we have both of our masses. So Venus's mass is 4.87 E24 kilograms. And we want it in kilograms. That's the correct units. Next, let's get m2. And m2 is the mass of the sun. And the mass of the sun was given to us in our problem. It's 1.989 E30. That is also kilograms, so it's the good units. Lastly, we need R. And R, just to remind you guys, because people keep forgetting, does not stand for radius. R stands for the distance of separation. So it'd be the center of Venus to the center of the sun. So this distance right here. Fortunately, it tells us that. It says the center of Venus is located this far away from the center of the sun. So I'm going to go ahead and rewrite that number down here. So we have 10816, and then followed by 4 zeros. 1, 2, 3, 4. If we want this to be in meters, though, we're going to need to multiply by 1,000, which means we're going to need to tack on an extra 3 zeros. Cool. Now that we have everything that we need, we can just take it and plug it into this equation. After we plug it in, we're going to end up with a force gravity that should be 5.52 E22. And since it's a force, it's going to be newtons. All right, number two, what is the centripetal force keeping Venus from flying off? We already answered that in our diagram right here. It's just force gravity. So now we can move on to number three, which is calculate the centripetal acceleration of Venus. So if we look up here, we have a few equations with acceleration in it. We have AC is equal to V squared over R, and that's talking about centripetal acceleration. But in order to use this one, we need velocity. We don't have velocity, so we can't use it just yet. So let's go ahead and use this one up here, which again is just Newton's second law. Net force equals ma, but A has been factored out. So we're going to go ahead and use that equation. So I'll just copy it down below real quick. Number three, we have A is equal to, and our equation is net force over m. All right, so what is the net force that is acting on our planet as it orbits around the sun? Well, the only force acting on it that's making it orbit is force gravity. So we can go ahead and replace net force with force gravity. And now the question is, what mass is experiencing this force and experiencing this acceleration? Well, it tells us to calculate the centripetal acceleration of Venus. So we're going to use Venus's mass here. We already know Venus's mass. It's right here. We just solved for it, or we took it from our problem up above. So I'm going to plug in M1 here. All I need to do is take the force that I just solved for, plug that in there, plug in my mass, and solve. I find out that the centripetal acceleration should be 1.13 e negative 2 meters per second squared. So this is a pretty small number. I mean, it's not really small, but it is pretty small. Number 4 says, what direction does the acceleration point? So the force is pointed towards the middle. We know that acceleration points in the direction of the net force. Since Fg is our net force for this problem, it's also going to be the same direction that acceleration points. So I would say that the direction is inward. Number 5 wants us to calculate the velocity of Venus. So let's look above if we have an equation with velocity. We have 2 of them. We got one right here, and we have one right here. In order to use this one, we need the distance and we need the time, which we can solve for the distance, but we don't have the time, so we can't use that. To use this one, we need the centripetal acceleration, which we just solved for, and the distance. So let's go ahead and take this equation and rewrite it down below, because that's the one that we're going to use. So for number 5, we have AC is equal to V squared over R. And I like to solve for the variable first and then plug in my numbers. So if we're trying to calculate velocity, we need to get velocity by itself. So we're going to multiply R over here. So we end up with R times the centripetal acceleration is equal to V squared. And then to get V by itself, you just square root. So let me simplify this so it looks a little bit nicer. We have V is equal to the square root of R times the centripetal acceleration. We said before, our centripetal acceleration is right here. We just solved for it in the previous problem. And our R is right here. Same R that we were using before because it is orbiting. So we're going to use this R again. Go ahead and plug those numbers into our equation. And we find out that the velocity that Venus is orbiting the sun at is about 3.5 e4. And it's a velocity, so it should be meters per second. Okay, number 6 says what direction does that velocity point? So that velocity is always going to point tangent. And tangent just means perpendicular to the middle. So right here, the velocity would point this way. If the planet was, say, over here, the velocity would point this way, so on and so forth. Number 7, calculate the period of Venus around the sun. And we want the answer in days. Okay. So if we're calculating period, that means that we're calculating time. And in order to solve for time, we need velocity, which we just got. But we also need d. D in this case is the distance that it travels. So the period would mean one full rotation. So we need to figure out how long this entire distance is. Well, we said before that that distance we can assume is kind of like a circle. So the distance is actually the circumference. And the circumference is just 2 pi r. So C is really equal to D. So let's combine these two really quick. So we have D is equal to V times T. And we also have C is equal to 2 pi r. And we know C is equal to D. So we're going to take this and plug it in for D over here. So we end up with 2 pi r is equal to V times T. If we're solving for T, let's just get it by itself. We're almost there. We're going to divide both sides by V. So now our equation is just T should be equal to 2 pi r over V. Let's take the variables that we had before. We know R because it's the same R that we've just been using. So we're going to take this big old R. I'll rewrite it. 1, 0, 8, 1, 6, and then a whole ton of zeros. 1, 2, 3, 4, 5, 6, 7. Okay. And then the V that we just solved for in the previous part, 3.5 E4. Take all this and plug it in, and we end up with our time. So the time that we get, since V is in meters per second and R is in meters, we're going to end up with a time in seconds. but it wants us to convert this over to hours. Actually, I think it's over to days. So let's double check. Yeah, so it wants us to give our answer in days. So whatever time we get here after we solve, we're going to take that number and divide it by how many seconds are in a day, which I don't expect you guys to know, but I do expect you to know that there are 3,600 seconds in an hour, and then there are also 24 hours in a day. So you can divide it by 3,600 and again by 24. If we want to simplify that now, we could also say that if we just wanted to divide it once, that there are 86,400 seconds in one day. So 86,400 seconds equals one day. So after doing all that math, we should end up with a period of 2.25 E2. And again, we converted everything, so we should have got days here. Last question we want to look at is, based off of our calculations, which planet travels faster around the sun, ours or the Earth? Well, this is 225 days, and we know that the Earth takes 365 days. So this should be pretty easy. We can see that ours takes less time, so our planet travels faster around the sun. So in this case, I would say my planet.